Hello and welcome to the second video accompanying Chapter 6 on the topic of the outer solar system. In this second video lecture, we're going to discuss asteroids, comets, and dwarf planets. And this is everything that isn't the Jovian systems, because the first lecture video was all about the gas giants and their moons. Okay, so this is everything else. It's going to be asteroids, comets, and planets like Pluto. All right. So kind of to get you started, since Pluto is kind of famous being a former planet that now has been demoted to a dwarf planet, or just also known as a Kuiper Belt object. This is what we used to know about Pluto back in 1930, when we could see it as a little dot with ground-based observatories. Once we got a telescope up into space, we were able to get images like this and see that there were some surface features, maybe some plains and craters and whatnot, but we couldn't make out much. But in 2015, when we flew by, we actually got these amazing high definition photos showing all the details of the surface of Pluto, and even ones much closer up, which we'll show a bit later. So it's been quite a journey, right, to get over 85 years to improve what we know about Pluto. And it is an amazing object. It's just not a planet. And the idea there is that if we had classified Pluto as a planet, we'd have like maybe 14, 15 planets. And we wanted to, kind of have a clear line between the really big true planets, of which there are 8, and then all these other objects, of which there are many, including ones much further than Pluto from the sun. Okay? Relative to the sun, that is. All right, so let's just move on, talking about small bodies, okay? So that is asteroids, comets, and dwarf planets. All right, so what's the difference between an asteroid, comet, and a dwarf planet? What are the meteors and meteorites? All right, so those are great questions. They're good kind of laying the groundwork of understanding the basics of this content. All right, well, this is a comet, okay? I can't mispronounce it, but Hyakutake, all right? And comets have tails, they're icy, but we'll talk about that, okay? So let's start with asteroids, okay? So key characteristics. Asteroids are rocky, okay? They're leftovers of planet formation, okay? So are comets, but the asteroids are the rocky ones. The largest is Ceres, all right? It has a diameter of about 1,000 kilometers, all right? There are 150,000 in the catalogs. There's probably over 1 million with a diameter of less than a kilometer, okay? But the 150,000 ones, these are ones, maybe 20 kilometers, 300 kilometers, there's lots in that size range, okay? Small asteroids are more common than large ones, okay? That's absolutely the case. That's really the case for any cosmological object. All the asteroids in the solar system wouldn't add up to even a small terrestrial planet. So their total size wouldn't even be close to Mercury, all right? And for that matter, it wouldn't be close to Ganymede, right? Because Ganymede, a moon of Jupiter, is bigger than Mercury, if you recall the last lecture video. Okay, so there's key things, all right? I think mostly what I want you to take note of is that they're rocky. If you remember discussing the frost line back in the previous chapter, that that we have this idea the terrestrial planets are inside of the frost line, where hydrogen compound ice can't form because it's just going to get basically turned to a gas due to the heat of the sun. And then you have things outside the frost line where you have Jupiter and Saturn and Uranus and Neptune, where hydrogen compounds can freeze into ices. That's where you have H2O ice, water ice. That's where you have methane ice and ammonia ice. And so that's the key idea, and that applies here to asteroids too, because asteroids are inside the frost line. Okay, to use a term from the previous chapter, which is just a general term to describe the solar system. Okay, so they're where those hydrogen compound ices can't form because they would vaporize, they would turn to gas. Okay, that's why they're only made out of rocks, because there's no ice to make anything out of. Make sense? Okay. Comets, on the other hand, they're formed beyond the frost line. They are icy. All right, so that's the difference. It's as simple as that. We got rocky small objects, asteroids, and we got icy small objects, comets. Okay, the nucleus of the comet is a dirty snowball, because remember, like I said about the gas giants, there's plenty of heavy elements out there. There's not like there's more heavy elements in the inner solar system. It's just that those heavy elements are greatly outweighed by all those ices. All right, same with comets. There's more comets. Comets can be bigger because there's just more ice to go around, right? But there's just as much rocky stuff. It's just mixed with the ice. All right, hence the dirty part. All right, most comets do not have tails. Okay, we'll talk about why that is. Most comets remain perpetually frozen in the outer solar system, because they're perpetually frozen because they're in the outer solar system. So if you can't tell, then tails only happen when comets veer into the inner solar system. Okay, so to give it away, although I'll state it in more detail, tails are just the consequence of comets boiling, basically vaporizing once they cross that frost line. But generally, comets don't cross the frost line, right? Because they can't have formed inside the frost line. So it's kind of unlikely that they're going to travel away from where they grew up, right? Where they formed. It can happen. They can get disturbed out of their orbit, and they can come sort of crashing into the inner solar system, right? Making a big tight loop, right? Only comets that enter the inner solar system have tails. That's it. End of story, right? All those comets that are way out past Pluto, they're just there frozen solid, okay? All right, and that's really a kind of a common misconception, right? Because people, they think, oh, all comets have tails. Not so, right? The ones that we see in the sky do because they happen to pass near Earth, right? That makes sense. We're inside the frost line. We're a terrestrial planet, right? We're in the hot part of the solar system. You get it, all right? So tails are huge, right? Here we can see the comet's tail is at least 2 solar diameters long, right? So it's like, it's twice as long as the diameter of the sun, so these are incredibly long, just trails of boiling away material, right? Their size is really quite remarkable, all right? And this is a sun-grazing comet, flying close to the sun, burning up as it goes, like Icarus. All right, and here's a third thing, dwarf planets, all right? So they are objects in the solar system other than planets which are round, okay? That seems like a silly definition, but that is spot on, okay? They're round. Everything we talked about so far, namely comets, asteroids, they're not round, okay? Now, as far as like categories, subcategories, if we were to do a Venn diagram here, there's a bit of crossover. You know how we mentioned Ceres, right? Ceres is an asteroid in as much as it's in the asteroid belt, but it's the only asteroid that's big enough to be round, and thus it's the only asteroid that is a dwarf planet. Now, is it still an asteroid? Yeah, because it's in the asteroid belt. It's formed from the same origins as all the other asteroids. So it's correct to classify Ceres as an asteroid, but it's also correct to classify it as a dwarf planet because it is round. It's big enough to have formed a spherical shape due to the gravitational pull because it's massive enough, right? There's enough gravity to do that. Basically, enough gravity to crush the rock into a circle. So that's the thing. That's what makes it a dwarf planet. It's a simple definition. Dwarf planets are round, asteroids are not, okay? Pluto is round, even though it's basically a comet. Other comets that aren't round aren't dwarf planets, all right? So Pluto's a dwarf planet. Eris, which is kind of out near Pluto, is a dwarf planet. Maki, another dwarf planet, further out than Pluto. Huamea, also a dwarf planet, all right? You get it. You get the idea, right? And most of them are similar to comets, right? All of these ones are similar to comets because they're all out where the comets live. The only dwarf planet that is similar to an asteroid is Ceres. So it's kind of cool, kind of special, all right? Okay, so large objects and their moons in the Kuiper Belt and asteroid belt, all right? So what are meteors and meteorites, right? What are they, right? Well, they're essentially asteroids that interact with Earth. Let's clear up the terminology, okay? So a meteorite is a rock from space that falls through Earth's atmosphere, all right? So it's the actual remnant that you would find in the ground, like in a crater, right? People collect meteorites. They're valuable, right? They might have rare elements in them, right? And they're just inherently rare. Not that many of them actually make it to the surface, okay? So that's what a meteorite is. The right part is kind of a geological term, right? It implies that it actually is the leftover rock, usually very high metal content in that rock, okay? So that's it. It's an asteroid once it's way out in space, and then it's a meteorite once it's landed on Earth's surface. In between those two events is the meteor, all right? And the meteor is actually kind of the event of the asteroid becoming a meteorite. It is the bright trail left over by the meteorite. So the meteor is what you spot in the sky. You're like, look, it's a meteor, right? So that's it burning up through our atmosphere because it's hitting at incredibly high speeds, maybe 20,000 miles per hour, right? It's coming in fast, okay? And so it comes in, it burns up in the atmosphere, and that trail is the meteor, okay? And that most of it won't make it to the surface. A lot of times, asteroids are just meteors because they completely vaporize in the upper atmosphere, and there's no meteorite left. Make sense? Okay. Here's a meteorite that ripped through someone's ceiling, okay, in Chicago, 2003. All right? So it's kind of a bummer, right? You got some real repairs to do, and it could have killed somebody, but, right, that's a good size meteorite there. That's valuable, all right? Sell it for tens of thousands of dollars to collectors, okay? So what's the difference between an asteroid, a comet, and a dwarf planet? Asteroids are leftover inner solar system objects. Comets are leftover outer solar system objects. Frost line, right? Okay, one's inside the frost line, others outside the frost line. Make sure you know which is which, okay? Dwarf planets are either of these, but they're large enough to be round, right? It's a great way to describe it, okay? So what are meteors and meteorites? They're the flashes of light on the ground and the remnants of objects entering their Earth's atmosphere, okay? All right, so let's talk more about asteroids. What are they like, all right? What do meteorites tell us about asteroids? And why is there an asteroid belt? That's a great question, okay? All right, so here's some cool example of asteroids, right? We got great giant Ceres over here, the true dwarf planet. Vesta's pretty big, but it's not quite a dwarf planet. It's too misshapen. And then you got all the ones in between, right? Like Eros, right? Just, about 30 kilometers long. Lutetia, all kinds of asteroids, okay? And this is just a tiny, tiny sampling, right? Some are fascinating just because, we've known them for a long time, Some are fascinating because they're very big. Some are fascinating because when we look at them and we calculate their densities, they seem to be made of valuable metals. And so we consider asteroid mining in the near future. So there's all kinds of reasons that scientists and entrepreneurs are interested in asteroids, okay? So asteroids are cratered. They're generally not round, right? A lot of these are potato-shaped, okay? All right, so asteroids with moons, yep. So some large asteroids have their own moon. The asteroid Ida, for example, has a tiny moon, Dactyl, all right? So essentially just a small asteroid gets locked in an orbital embrace with the larger one and just slowly orbits around, right? So the microgravity of Ida is enough to have a very slow, close orbit of essentially a rock, right? Just something that's, like a few hundred meters across, okay? So what's cool about that is asteroids that do have moons are great for studying because we can actually calculate the asteroid's mass in a way we couldn't have. We can use, what can we use? We can use Newton's synthesis, right? This is a throwback from a much earlier chapter. Newton's synthesis of Kepler's third law. Okay, bonus points if you remember that. Okay? So that's how they do it. We have discussed how to do that. All right, so the mass and size tells an asteroid's density, okay? So there you go, right? Because we can find the size just by looking at it, okay? We just we just know its distance, and then we see how much angular space it takes up. Some asteroids are solid rock, others are just piles of rubble, okay? All right, some are mostly metal. Okay, so looking at Vesta, right? Well-known asteroid, a Dawn spacecraft flew by, so we were able to get some close-ups. Okay, so it's much wider across one side, right? South Pole view, equatorial view. We got some interesting, kind of stretch marks across the equator. Lots of cratering on certain sides. Okay, evidence of a huge impact that gouged out a big piece of it, like a big piece broke off, right? Kind of cool to imagine at some point. All right. Here we see Ceres, also which was observed by a flyby from the Dawn spacecraft. We can see some giant craters. We can also see these really interesting thing here, right? This big mountain. It's obviously there's some sort of geological activity, maybe some kind of ice volcano, that was pushing up to the surface. Not sure if that happened billions of years ago or more recently, but really fascinating. It's that Ceres, at least at some point, wasn't geologically dead. After all, it is big enough to be classified as a dwarf planet, so we should maybe expect some geological activity. It had some core to it at some point, enough leftover heat from its formation. Okay, so why are there very few asteroids beyond Jupiter's orbit? Okay, you know the answer. Talked about it. Think about it. Okay. All right, because ice could form out there, and it probably seems like, wait, how's that the answer? Because all the ice out there past Jupiter's orbit meant that everything that wouldn't have been an asteroid instead became a comet because it got encased in ice. So in a sense, a comet is just a bigger asteroid that got encased in ice. Now, it's not like there's just a solid core. It's kind of a mix of rocky material and ice, sort of evenly distributed throughout the body of the comet. But that's the idea. When you have ice, you just can't have an asteroid. In the story. Okay? All right? So this picture comes up a lot, right? These kids love this giant rock here, right? It is pretty cool. Okay, so meteorite types. Primitive, all right? They have been unchanged in composition since they first formed 4.6 billion years ago. And then there's processed meteorites. Younger that have experienced processes like volcanism or differentiation. And the reason we want to talk about these two is, remember how we talked about dating the solar system? So, and looking at the radioactive decay of certain isotopes in meteorites, that we could collect here on Earth, that it made it to Earth's surface. Well, to do that and actually get a date for the origins of the solar system, where we come up with that 4.5 billion years, we need the primitive type of asteroid. Because there's ways to tell them apart, on our best guess and based on sample sizes of looking at different meteorites. And so we're pretty sure we can tell which ones are the primitive ones, and they consistently have dates that when we date their isotopes of about 4.5 billion years, okay? And that's cool, right? And we can, and it's been kind of confirmed through multiple meteorites. But on the other hand, there are other types of meteorites. Those are ones that are coming from other planets that have been, melted and remelted and reformed, and thus the isotope concentrations have been reset. Like, how we talked about Io being the most volcanic object in the solar system? Well, it can spew rocks away that have velocities greater than the escape velocity of it, right? So they're so fast that they actually permanently leave the gravitational pull of Io. And some of them then might crash to Earth, millions of years later, or even sooner. And then we look at it, we realize that the asteroid is not primitive. I mean, we guess maybe it came from Io based on its particular mineral content, and then we can date how old it is. And it wouldn't tell us anything about the age of the solar system, but it'd be interesting in its own right, okay? So that's a type of processed meteorite, okay? So here's some examples. Here's a stony primitive meteorite. Here's a carbon-rich primitive meteorite. So, there's kind of different types. Here we have a processed meteorite, okay? This one came from a shattered asteroid's core, okay? And then this one came from probably came from Vesta's south pole. We talked about how there's a big missing gouge out of Vesta, all right? So these are process types. They went through some melting and reforming at some point. Okay, so meteorites from the moon and Mars absolutely can happen. So a few meteorites arrived from the moon and Mars. The composition differs from the asteroid fragments. And so it's a cheap but slow way to acquire moon rocks and Mars rocks. We don't have to fly there. We can just wait for them to come to us. Okay, all right. But we can also fly there, all right? And we have actually landed on asteroids, collected samples, and came back to Earth. All right, so sample return missions to asteroids provide material to compare with meteorites. And that's pretty important, and that's pretty recent that we've been able to do that. That really confirmed our models, and it confirmed our hypotheses, because we were really able to see that, yeah, this rock is in fact the same type of rock that from an asteroid. And by this rock, I mean a rock that fell down through our atmosphere, and we looked at it, and we looked at its particular unique chemical composition, and then we go to asteroids in the asteroid belt and collect rocks, and they match up. All right, so we can really, we can say, oh, well, this rock isn't, just coming from Earth or coming from the moon or something. It is indeed coming from the asteroid belt. Okay, all right, but there's an open question here, right? There's an elephant in the room. Why do we even have an asteroid belt? All right, now this is another one of those great misconceptions. As a lot of people love to say that the asteroid belt is a planet that was destroyed. There's another world like Earth or something that was past Mars, and it got blown up at some point, and so this is all the remnants of that blown up planet. All right, and that's fun to think about. That's great sci-fi, right? But it's totally untrue. The asteroid belt never formed as a planet, and the reason is this right here: Jupiter. All right, Jupiter prevented a planet from forming there. How? Well, let's talk about it. Okay, so which explanation for the belt seems the most plausible? Okay, well, it's that the belt is where the asteroids happen to survive. All right, so that obviously leaves some other open questions, but as far as a plausible start, that's a good start. Okay, all right, so here it is. It's all about orbital resonances. And we actually discussed this in the last video for this chapter. Orbital resonances came up when we discussed the three closest of the Galilean moons of Jupiter: Io, Ganymede, and Europa. All right, Callisto is too far out to be part of the resonance, but those three closest moons, they absolutely have this resonance. They line up every so often, okay? So that's kind of the same idea we're talking about here, all right? So asteroids in orbital resonance with Jupiter, because there's going to be some, experience periodic nudges. Eventually those nudges move asteroids out of those resonant orbits, leaving gaps in the asteroid belt, all right? So notice, right, here's Earth, here's Mars, and notice that this horizontal axis is an orbital periods measured in Earth years, right, for kind of easy perusing, okay? On the vertical axis is the number of asteroids. There's not a lot of asteroids that share our orbit, nor Mars's orbit, but once we go out past Mars, we start to see, oh, well, this is where the asteroids are. We have lots of them, right? Thousands of asteroids in these particular regions of the solar system. But there's these really noticeable gaps at even fractions of Jupiter's orbit. All right, So this is a fraction of 1 over 1, which so Jupiter's orbit is just a little bit less than 12 Earth years, all right? It's period. And so then if we take that fractions of Jupiter's orbit, then we see exactly half, all right? Yeah, there's a gap. And then definitely a third, right? That one's so obvious because like everything to either side of the 1/3 resonance with Jupiter is, I mean, that's like peak asteroids, right? There are a ton of asteroids at that particular distance from the sun. But then there's almost none at the point of 1/3 because that 1/3 means that every, so let's see, it'd be that these ones, if they have 1/3 the time, that they're going to line up with Jupiter 3 times for every time that Jupiter makes a full circle around the sun. All right, so 3 times per Jupiter year, which is basically so Jupiter is about 12 Earth years, and a third of 12 is 4. So there it is, right? So about every 4 Earth years, asteroids that used to be this distance from the sun line up with Jupiter, and that means pretty frequently they're lining up with Jupiter and getting pulled towards Jupiter. Now, most of their pull is obviously towards the sun. That's what keeps them in orbit, after all. But every 4 years, which is pretty darn frequent, there's a little pull, and then another little pull. And so over millions of years, over tens of millions of years, over hundreds of millions of years, that periodic pull every 4 years adds up. And that means that those asteroids, they get pulled away. Now they're no longer in that region. There's just a gap. And that gap, what else does it make you think of? The rings of Saturn, right? And the rings really of any jovian planet, but in particular the very bright, noticeable, reflective rings of Saturn, and those gaps, because those were also from resonance. And that's why the ice doesn't exist in the gaps, okay? And sometimes because of shepherd moons and other effects, but also because of resonance with Saturn, all right? So that's the idea here, is that because of these gaps in a region where otherwise there probably would have been enough mass to amalgamate together and then eventually accrete into a planet, it couldn't happen because there's these weird missing spots. So the matter was never able to form the big enough chunks and then start pulling itself together into even bigger chunks in this sort of like cascading effect, the snowball effect. And don't think frost sign, this is just the snowball as in the analogy, right? Because you roll a snowball down a hill and it gets bigger and bigger because as it gets bigger, more snow can stick to it and so on. That's how Earth formed. That's how Mars formed. That's how Venus formed, right? That's called accretion. Go, refer to the previous chapter. So that idea would have worked in the asteroid belt. There was enough matter. It wouldn't have been a giant planet, but there would have been a planet where the asteroid belt is. But Jupiter prevented it from happening due to orbital resonance. End of story. All right. All right, but let's look at a couple more slides to elaborate on it. Okay, you got my take on it. Let's put it in writing. So, all right, rocky planetesimals between Mars and Jupiter did not accrete. That's that word, accretion, into a planet. Jupiter's gravity, through influences of orbital resonance, stirred up asteroid orbits and prevented their accretion into a planet. Okay, because it created gaps. All right, so what are asteroids like? They're rocky, small potato-shaped leftovers from the era of planet formation. All right, and the reason we have a place where they never formed the planet is because, first of all, there's primitive and processed, and the reason we have a region where they're still left is because of Jupiter. So that's one of the legacies of Jupiter is the asteroid belt. Okay. All right, let's talk about comets. So why do comets grow tails, and where do they come from? 2 simple questions. All right, I love it. Right, this second half of the chapter has really straightforward questions. Sometimes the answers aren't that straightforward, right? But very straightforward questions. All right. So first of all, there's something called the nucleus of the comet. This is just what comets are when they don't cross, sunward of the frost line. It's just a dirty snowball, right? It's just, that's kind of a weird name for it, but it more makes sense. It's just this, right? This is the nucleus. It looks a lot like an asteroid. It is a solid object, but it has a lot more ice. It's much softer, right? And it has some really powdery sections because it wouldn't be very packed down necessarily, at least not all of it. And it's got rocks mixed in there, but that's it. That's what a comet is as they float around through space. All right, and this it is the source of material for a comet's tail because all of this can start vaporizing as it gets heated up. Okay, so this is a mission, a space mission. So it was a mission to study the nucleus of a comet called Tempel 1. The projectile hit the surface on 2005, and then many telescopes studied the aftermath of the impact, so we can actually see like there was a big amount of light as it crashed into the comet. All right, so this is one of our interesting missions out there to explore comets. Okay, so let's talk more about comets. So a coma is the atmosphere that comes from a comet's heated nucleus. So when a comet isn't heated, when it's out in deep space, well past Jupiter, there is no coma. But as a coma forms as a comet, the minority of comets, but as a rare comet is in some sort of orbit that brings it closer to the sun, okay, and it's heated up. All right, so now let's get into the tails, and we'll talk about it more in the next slide. We have a plasma tail, which is gas escaping from the coma, that atmosphere, right? There's of course atmosphere on a very small scale because comets are nowhere near the size of planets, right? But a plasma tail is gas escaping from the coma, pushed by the solar wind, okay? A dust tail, on the other hand, is pushed by photons. Okay, so there's a bit to unpack there, right? But there's two tails. Notice here, right? Well, it turns out there's a third tail. I'll mention that as well. But here's the dust tail and the plasma tail. All right. So we're talking about these two tails first before we talk about that mysterious third tail, which I just mentioned, because these are the ones you actually will see when you look at a comet, right? So the famous comets you can see with the naked eye, or the recent one you could see with a basic telescope. They'll often have two distinguishing tails, especially the biggest, brightest ones. The ones that are really hard to see, that you can't really clearly make out the two, but the biggest, brightest comets that will be visible in the sky will have two tails. And you might be like, I've never seen a comet in the sky. Well, it's not that common, right? You can have a decade or more go by before there's a comet. And we don't necessarily know they're coming. Often astronomers don't know there's going to be a big, bright, visible comet until a few months before it happens, okay? Other times we might have more warning, but it's kind of interesting. And then the ones that were famous, like the ones like Halley's Comet or something that everyone saw. I can't think of the exact time. Let's say I know there's some famous comets in the 90s. Okay, when I was like younger, right, teen years or something. So those comets like that, they're not going to be back for like hundreds of years, right? So once we know a comet, you're not going to be alive to see it again, because often their orbits take a long, long time, hundreds or even thousands of years. Okay, but here's a good picture to show the different tails, to clearly show all three of the tails. Okay, so first of all, here we have a comet far from the sun. Good point to start, because this is when they're frozen. This is most comets most of the time. All right, there's no coma, there's just a nucleus, and it's outside of the frost line. Imagine this dotted line is the frost line. Okay, all right. But as a comet comes inward of the frost line, it forms a coma. That's kind of the first thing. As it starts to heat up, those hydrogen compounds start to vaporize, because it's basically they're boiling. And you might be like, wait, space is really cold. How do you boil? Well, that's because space also has really low pressure, so you can boil at very low temperatures as long as you have really low pressure. And that's what happens is those hydrogen compounds on the comet start to boil away, kind of forming gas. That gas is gravitationally kind of sticking to the comet for a while, right? But then as the comet starts to pick up velocity, as it gains kinetic energy and loses potential energy as it comes in closer to the sun, well, now that atmosphere has inertia and it starts to kind of lag behind the comet, and that's the tail. That's the big tail that's left behind. Okay? So let's look at the directions here. So here we have, I'm going to zoom in on one so we can clearly see the different directions. Here we can see the plasma tail. The plasma tail points straight away from the sun, okay? Because it points in the direction of the solar wind. The solar wind is a barrage of charged particles that's leaving the sun. So it is formed primarily of electrons, all right? Electrons, some positrons, right? But let's just say for simplicity, it's primarily formed of electrons, okay? And it's a big deal. We talked about it briefly when we talked about the magnetic fields and magnetosphere. Magnetic fields like ours, or all the jovian planets that have very large magnetic fields and corresponding magnetospheres. Those fields, those magnetic fields, they redirect the charged particles, which is really important for, say, maintaining an atmosphere, creating the conditions for life, and so on. Okay, so that's great, right? That's the solar wind. All stars create it. Our sun is no exception. Okay, now, but there's something else. There is a dust tail, and those particles, they're not being pushed away by the solar wind, Because they're not charged. So notice the plasma tail, if it's being interacted with by the solar wind, well, the only way, and this is a physics thing, but the only way for a charged particle to exert a strong force on something is for that something to also be a charged particle. So in other words, electrons repel electrons, electrons attract protons. And so that means that the plasma tail must be formed of charged particles. Well, just the word plasma actually implies that it is formed of charged particles, because plasma is an ionized gas. Ionization means that you're missing electrons. So whatever were the molecules in the surface of the comet, some of them, in the process of boiling, lost their electrons because they were boiling very energetically. And in doing so, they became a plasma. They became an ionized gas. Now that ionized gas is charged. Okay, it has a net charge. That net charge then interacts with the electrons, the solar wind. And it interacts in a really strong, it's a very direct force. Furthermore, the plasma is formed of very, very light particles. So the force is much greater than the mass. Okay, thus the acceleration is so great that the tail points straight away from the sun. Okay, all right, so I'm kind of going into the details here, but I just want to point straight away. Charged particle interaction, tail points really directly away from the sun. All right. On the other hand, the dust tail also points away from the sun, but kind of like at an angle. Well, that's because it's dust. It's formed of bigger particles. The bigger particles have more mass, so they're not pushed quite as easily. They're still pushed, but not quite as easily. Now, here's the thing. If it's formed of dust, what does that mean? Well, first of all, that means it's not ionized. This is neutral dust, so it has no net charge. So how do you push something that has no net charge? Well, you could physically push on it, right? You could just go up and push it. Now, that's usually like an electrostatic force that allows objects to be solid in the first place, but that's a story for another day. Now, you could also push on it with gravity, but gravity would actually be towards the sun, so that can't be the explanation. So the push is actually from the sunlight. Now, there's a lot to unpack there that I'm actually not going to get into, but the point being that photons, which are particles of light, different than the solar wind, because the solar wind is composed of electrons, but light itself is composed of these particles called photons. They're very unusual particles, but they are light. Light is photons. Photons are light, okay? Light is a wave, light is a particle, duality of light. Yeah, bit to unpack there, right? Big stuff in physics. But the point is that photons are particles, and they can push things. So light can actually exert a force. It has medical applications. There's these things called optical tweezers where medical researchers can pull apart little proteins being like the building blocks of kind of tissue, and they can pull apart proteins with lasers, essentially, which they call optical tweezers. So I just bring that up because that's an idea, a really direct idea of light applying a force. A laser actually being able to act like a tweezer. Okay, so that's what's happening on a much larger scale here. Is light is physically pushing these neutral dust particles. Now the dust is bigger and is being pushed by something that doesn't push as hard. Because here, the plasma was a strong electro force. Okay? Here, this is kind of a lighter force from the momentum of the sunlight. And that means that the tail is bent. It's bent because it's less force and it is bigger particles with more mass, thus more inertia. Okay? All right. Now, finally, I just can't help but get into this stuff. Physics is my background. I love getting into these details. But finally, we have the third tail. Okay, the third tail is invisible because it's not very reflective, and it's also not nearly as long or as thick. But the third tail is composed of large particles that are completely unaffected by the sunlight or the solar wind. How so? Well, they're so large that the photon pressure, the solar radiation pressure, just isn't enough to affect them. They have plenty of inertia, so they just kind of continue on their way. And they're neutral, so the solar wind can't affect them. Okay, and so these are things that are maybe many centimeters across. These are the big chunks that break off. Well, the big chunks that break off, they get left behind. All right. So the comet is continuing on its way, but some of these big pieces, they're going to have some like drag force due to the atmosphere, and they just kind of get left behind, and they linger in the orbit that was the comet's orbit. So this tail is invisible to observers on Earth, and kind of maybe seems boring, right? Why do we care about this large particle tail here? Okay, well, we care about it, and notice that it directly follows the path of the comet's orbit, right? It's just remnants, left behinds. But what's so interesting about this last tail is it is the progenitor of what's the term I'm looking for? Where you have meteor shower. That's it. It is the progenitor of meteor showers, because what happens is this leftover third tail is going to drift into Earth's orbit, and then Earth, maybe a few months later, will pass through that tail, and that's a meteor shower. So that's how these meteor showers are always known on particular calendar dates of the year, because there's all these leftover tails from previous comets that last for decades or even hundreds of years. And as Earth passes through those leftover tails, those leftover large particle tails from a comet, we have a meteor shower every time, because we're passing through a region of space where there's a bunch of leftover junk. All right, a few centimeter across rocks that came off of a comet. Pretty cool, right? All right. So, watching a comet become active, this is the idea of the coma heating up. This was from another comet mission called the Rosetta mission, Comet 67P. So you can really see how the surface starts to boil. All right, pretty cool. All right, here's a jet. All right, that's actually this charged gas coming off of the surface of the comet. It's like boiling away. It's really neat. So comets eject the small particles that follow the comet around its orbit and cause meteor showers, where Earth crosses the comet's orbit. All right, and the meteor showers always appear to emanate from a single point, because it's like driving into a rainstorm. And it looks like the rain's all coming from a single point. That's because you're entering a region of particles. All right, in this case, the Earth. Right? Here's the analogy: driving into a rainstorm, looks like all the rain is kind of coming from a single point, which is just the direction of your velocity. Same thing for Earth, right? And so you're just passing into all those leftover particles, those leftover rocks from the comet's path, and then it looks like they're showering down on us. Okay. Where do they come from? Okay, we haven't discussed this yet, but where do comets come from? All right, well, there's two answers to that. Okay, so only a tiny number of comets enter the inner solar system. I mentioned that a couple times, right? So most of them never enter the solar system. They're just out there in the deep, faraway reaches of the solar system. Most stay far away from the sun. Okay, and here are the two places where they exist in huge numbers. First of all, the Oort cloud. Okay. The Oort cloud is huge. It's way out here, okay? It's unbelievably far from the sun, and it has comets in random orbits that extend out to 50,000 astronomical units. So to put that in comparison, I mean, Neptune is like 60 astronomical units from the sun, and that's really far. Now, imagine multiplying that by 10 to get 600 astronomical units, and then multiplying it by 10 again to get 60,000, right? So it's 100 times further approximately from the sun than Neptune, which is also already really far from the sun. All right? So you can think of it as maybe 80 times further from the sun than Pluto. I mean, that's incredible. We've never sent a space probe even close to that far. So that's why the Oort cloud is actually still a theoretical construct, because we never confirmed its existence. But we seem to, see comets that come from it, so we suspect it's out there. Okay? Then the other closer, more kind of maybe normal type part of the solar system is the Kuiper belt. And the Kuiper belt is basically, you can think of it as kind of starting with Pluto's orbit. So it's everything past Neptune. And it has orderly orbits, so counterclockwise as viewed from above the ecliptic plane, like everything else that orbits that way. It's usually highly elliptical, but definitely in planar orbits. Okay, so that's what we say orderly orbits. And that's 30 to 100 astronomical units away. Okay, all right, so there you have it. Okay, so the Kuiper belt comets formed in the Kuiper belt, flat plane. Okay, just like the planets all form a flat plane. That's the ecliptic plane. They're aligned with the plane of the planetary orbits. Yep, orbiting in the same direction as the planets. Yep. Okay. On the other hand, the Oort cloud comets were once close to the sun, but they were kicked out of the orbit by gravitational interactions. That's what all these theoretical models suggest. Is there was a period early in the solar system where the gas giants were forming, and they were constantly kind of flinging comets out. And essentially those comets would lose all their kinetic energy and just drift to the very edge of the gravitational influence of the sun. And that's why we think that there's that kind of almost a sphere of almost resting comets. Not very close together, right? Very, very, very dispersely spread apart. But at the, way out in deep space, there's this sphere of resting comets. Okay? All right, it's a spherical distribution, and they orbit in every direction. And by orbit, we mean really, really slowly. I mean, a comet that far away in the Oort cloud would have an orbit that literally takes hundreds of millions of years to orbit the sun. Okay, first of all, they're very slow, and second of all, it's a long circumference. Okay, so we talked quite a bit about why they form tails. I think we're good there, right? Where do comets come from? Two places. Okay, Kuiper Belt. We have probes that are currently traveling through the Kuiper Belt. Right, it's much closer, but still about 1 billion kilometers away. Okay, and then the Oort cloud, this very, very distant place that we only theorize exists, but hopefully will someday confirm its existence. Okay. All right, now let's talk about Pluto and more about the Kuiper Belt. So, because so far we mentioned the Kuiper Belt and it's got comets, but it's got dwarf planets, right? Makemake and Pluto and Eris, right? So let's talk about it. All right. So here's the idea: Pluto will never hit Neptune. Right, here's Pluto, by the way. So Pluto will never hit Neptune, even though their orbits cross because of their 3-2 orbital resonance. Hey, orbital resonance again! Woohoo! Okay. So the idea is that they do like their orbits like definitely cross over, but they won't hit because they have sort of synchronized orbits. Okay, but that actually is interesting because it goes to show that Pluto sometimes is closer to the sun than Neptune. All right, you might be like, wait, shouldn't Pluto be a planet then? But it's not about distance. It's about the fact that Pluto is, first of all, too small to be a planet, and second of all, it hasn't completely cleared its orbit. So it shares its orbit with other comets and Kuiper Belt objects, and therefore it can't be classified as a planet. All right. All right. So here we're looking at Hubble's view of Pluto and its moons. All right. There's Pluto. All right, and it's got quite a few large moons. Whoops. Including Charon, which is almost as large as it. All right. So what is Pluto a planet? Well, it's much smaller than the terrestrial Jovian planets. It's not a gas giant like the other planets. It has an icy composition like a comet, essentially like a really large comet. It has a very elliptical orbit. It has an inclined orbit, so it's still in the ecliptic plane, but significantly inclined relative to it. And it definitely has more in common with comets than the 8 major planets. All right, its moon Charon is nearly as large as Pluto. Sorry, it's probably made by a major impact, kind of like our moon. Okay. Our moon was theorized to be made by a major impact. It's very cold, 40 degrees Kelvin. That is incredibly cold. Remember that 0 Kelvin is absolute zero. So 40 Kelvin is very cold. Pluto has a thin nitrogen atmosphere that will refreeze onto the surface of Pluto as Pluto's orbit takes it further from the sun. So it's almost like a comet, right? It has like a coma so an atmosphere that forms and then disappears throughout its very long Pluto year. New Horizon passed by it recently, just a few years ago, and showed a lot of very interesting things, including active geology, right? Because Pluto is closer right now than it will be in other parts of its orbit, and during this phase of its orbit, there's basically like ice volcanoes and ice like ice flows and so on. Some really interesting stuff happening, and we don't fully understand. All right, so here are the amazing recent photos of its surface. We can see it has mountains as tall as the Rockies, probably made of water and ice. It's really amazing. Right, and even at 40 degrees above absolute zero, there are nitrogen ice flows that are apparently like flowing. Right, we can actually see the evidence, kind of like deltas. Okay, and here's Pluto's thin atmosphere. You can actually make out the atmosphere, the remnants of the atmosphere. Right, look at these like frozen mountains. Okay, on the surface of Pluto, amazing. All right. We can also see smooth regions that resemble the lunar maria, suggesting eruptions of lava. But lava here wouldn't be rocky lava; it would be like icy lava. All right, which might just be water. Okay, but still like eruptions of melted material coming up from beneath the surface. Okay, covering up previous craters. So Pluto is not covered in craters, right? And that's the thing. And if you kind of see a connection here to how we talked about how the icy moons of the Jovian planets tend to have a lot more geological activity than say like our own moon, even though our moon is so much closer to the sun. That's because ice melts at such a much lower temperature than rock. And so you can get a lot more geological activity when your composition of your planet is mostly ice as opposed to mostly rock. All right. So Pluto's size was overestimated after its discovery in 1930, and nothing of a similar size was discovered for several decades, which is why it was classified as a planet for so long. Now other large objects have been discovered in the Kuiper Belt, including Ceres, which is in the Kuiper Belt and is quite large. And then the International Astronomical Union, the IAU, now classifies Pluto and Eris as dwarf planets. And that was kind of when their hand was forced, this IAU, because they either had to make Eris a planet and have 10 planets, or make Pluto not a planet anymore. And they decided on the second decision and declassified Pluto as a planet. Dwarf planets have not cleared most of the objects from their orbital path, and that's part of the official definition of dwarf planets as opposed to normal major planets. All right, so it's an icy world with mysterious active geology. And then why is there a Kuiper belt? Well, it's made up of leftovers from the planet formation era, and it's shaped by interactions with the Jovian planets. Okay, so in another, you know how we said like the asteroid belt exists because it was never able to form a planet thanks to the resonance with Jupiter. So you might ask the same question. Well, if the Kuiper belt's a belt, why did it never form like another Neptune or something? Well, because it's such a large region. It's so much further out. As you think about it, as you like form concentric circles that are the orbits of the planets, and you get, here's the sun, right? And as you form these larger and larger circles, they get bigger and bigger. So then the matter that populates those larger and larger circles starts to be more and more spread out. So eventually, when you get further enough away from the sun, further to Neptune, the matter is just too spread out to ever accrete together to form a world. And that's the story of the Kuiper belt. So you don't need any other explanation besides the fact that it's just so far away. Therefore, there's no planet. Okay? So let's talk, our last topic here, about collisions. What's the danger of objects crashing into Earth? How did the dinosaurs die? And what's the risk of impacts today? All right? So here is a string of violent impacts that happened on Jupiter in 1994. So really showing how an asteroid or a comet can rain down on a planet. If this happened on Earth, it'd be catastrophic, right? So this is a huge collision, right? So, we talk about that era of bombardment that happened during the first 500 million years of the solar system and how that, shaped the surface of worlds that haven't had much activity since, like Mercury. But, it wasn't just the first 500 million years. There are still big leftover objects that can smash into planets and create really big effects, right? Even as recently as just a couple decades ago. All right? And in this case, the tidal forces tore it apart during a previous encounter with Jupiter, and then it broke into a few pieces and rained down, right? Okay? Here's the kind of showing a artist's conception of that impact as those big pieces fell down to the surface. Huge amount of energy was released. And this would be like viewing it from the surface of Io, right? This is like if you were standing on Io looking at Jupiter. Okay? All right, here's looking at an infrared, seeing all the energy that was released as they crashed into the thick atmosphere of Jupiter. All right? So the black spot in this photo is a scar from the impact of an unknown object that struck Jupiter more recently in 2009, right? Just ripping through the clouds of Jupiter. It must be kind of cool as an astronomer to be like, whoa, there's some big rip in the clouds of Jupiter. Okay, so did a big impact kill the dinosaurs? Okay, couple hundred million years ago. All right, well, fossil record shows occasional large dips in the diversity of species, mass extinctions, it's a term for that. The most recent was 65 million years ago. All right, I said a couple million, but that's more. Dinosaurs were wiped out more recently, 65 million. That ended the reign of the dinosaurs. So iridium, so here's the kind of the evidence. Iridium is a very rare element here on Earth, okay? But it's often found in asteroids, or meteorites rather. Okay, well, asteroids as well, but we can confirm its existence in meteorites. And a couple of scientists, father and son, Alvarez, found a worldwide layer containing iridium that was about 65 million years old, right? And that's really where the theory came from. Is it why is there this kind of like this dust layer of iridium? And it would have been explained by a rather large, meteorite striking the Earth and releasing a huge amount of energy and vaporizing a bunch of its composition, including iridium, and then that ash raining down over decades, also causing huge climate change because it basically, drastically changed the temperature and the weather of the world for quite a while. All right, and dinosaur fossils are all below that layer. So it's there could have been other causes, but that wouldn't have helped in terms of keeping dinosaurs alive. All right, so here we have the idea: no dinosaurs fossils above the layer. Here's the rare element, the iridium layer, and this is where all the dinosaurs fossils are. Right? And you can. This isn't just one place on Earth. You can look at anywhere where dinosaur fossils are found and find this type of division. Okay. So the meteorite that would have done this would have had to be 10 kilometers across, so huge. It would have sent a large amount of debris into the atmosphere. That debris would have reduced sunlight reaching Earth's surface, resulting in drastic climate change. Okay, and that could have been the cause for mass extinction. Because we had this type of animal that dominated over the world, and they were the largest. They were like the peak of the food chain. And so if there's a huge disruption to the weather, the animals that are going to affect it the most are the ones at the peak of the food chain, right? And so that's, whereas, obviously like, the bacteria and all the small organisms could survive, but the giant herbivores and the predators are not going to be able to. Okay? And what? We need a smoking gun, right? And geologists think that it's right here in the Yucatan Peninsula because they can see a huge crater that dates to about the right time. Okay? So that would be the impact site right there, the Yucatan. Okay? So a comet or asteroid about 10 kilometers, so they were not sure, right, what it was, whether it was a comet or asteroid. About 10 kilometers in diameter would approach the Earth and crashed, releasing a huge amount of energy. Okay? Could that happen today, right? Is there something that's going to come and wipe us out? Maybe, right? So how great is the impact risk today? Well, asteroids and comets have hit Earth. Okay? A major impact is only a matter of time. It will happen. It will, right? There's no possible way, right? Take, say, another 65 million years. Who knows if humans will be here another 65 million years. But there's no possible way that there won't be some impact in that period of time. Will there be one as big as one with dinosaurs? Well, not necessarily, but it's just a likelihood game, right? As in the longer you go, the greater the chance. The same, kind of like with earthquakes, right? There always will be giant earthquakes. It's just a matter of time. Okay, so however, major impacts are very rare. We can already tell we're talking millions of years, right? Extinction level events happen millions of years apart. Okay, major damage happens tens to hundreds of years apart. Okay, so here is Tunguska, which is in Siberia in 1908. An impact released a huge amount of energy that just knocked over a bunch of trees because it basically releases like a shock wave of energy, kind of like a nuclear blast, and then energy just levels everything in its path. So a 40-meter object, okay, so 40 meters, not nearly as large, but still quite large, disintegrated and exploded in the atmosphere. All right, and here is in 2013, also in Russia in Chelyabinsk. All right, and this one came in. This one actually didn't do that much damage because it came in at an unusually kind of like horizontal angle instead of coming in steep. You can see it came in very, this picture could be deceptive in terms of the angle, but it did turn out that actually was a very non-steep angle. And so it spent a lot of time burning up in the atmosphere, but did eventually have like a big explosion up in the atmosphere, which did release a great deal of energy. Okay, so here's kind of the likelihood, all right? So if we look here on the horizontal axis, we have impact size, all right? So this is crater is about 10 times larger than the size, by the way. This is the size of the asteroid. Well, I should say of the meteorite, okay? Because it's kind of the leftover part that isn't burned up, all right? So a 10 meter meteorite would have a crater that is 100 meters. A 100-meter meteorite would have a crater that's a kilometer across, 1,000 meters. That's pretty large, right? Okay, and let's look at the likelihood. Let's think about that 10-meter meteorite that has a 100-meter crater. Well, we should expect one of those about every, well, somewhere between 100 years and 1 year. Okay, so maybe every 50 years. Okay, all right. On the other hand, how often should we expect a meteorite that's 100 meters across that has a 1 kilometer crater? Well, that one's gonna be less likely. That'd be right here. Well, that should happen, well, somewhere between 1,000 and 1,000,000 years, so maybe about 10,000 years. Because notice this is a big difference, right? 1,000,000 and 1,000, that's a huge difference. That's 3 orders of magnitude. And so, so having a crater that size, much less likely. As we get into the really big ones, the ones that can cause mass extinction, right? Like the 10 kilometer and the 100 kilometer, right? These huge ones, like a 100-kilometer one. I mean, that'd be mass extinction, like almost, like every living, creature on Earth type of mass extinction. Well, the likelihood once in Earth's history for this one, this is probably like the kind of one that formed the moon. This is the kind that wiped out the dinosaurs. And we can see that only happens maybe every 200, 400 million years. Okay? Are we due for one? No, not necessarily, right? Do we have to be on the lookout for them? Yeah, we should be. Okay? So we, right? Where is it, right? Where's the one that's going to wipe us out? Well, we haven't found one yet, right? There's no impending doom that we know of. Deflection is more probable with years of advanced warning, so we should really work on our techniques of advanced warning and think about what we would do in order to save humanity if necessary. Control is critical. Breaking a big asteroid into a bunch of little asteroids is unlikely to help. Okay, so we have to think of some other. We can't just blow it up. All right, and we get a less advanced warning of a killer comet, because one of those comets that come from the Oort cloud, those have the random orbits. So they can really come from any direction. So the thing about asteroids, we can look in the ecliptic plane and narrow our search. Not so of comets. So if something's really going to come out of nowhere and wipe us out, it's probably going to be a comet. All right? And there's a website that you can go to and actually look at all the current data about impact. So we'll talk about how close they're going to be and what the risk level is, and it's updated every day. It's really cool. All right? So last idea here, how do the jovian planets affect impact rates and life on Earth? Well, they actually help redirect asteroids. So the gravity of the jovian planets, especially Jupiter, can redirect a comet. And Jupiter has directed some comets towards Earth, but has ejected many more into the Oort cloud. So it's kind of it's a two-sided, it's a double-edged knife here. So on the one hand, Jupiter can cause more impacts because it will send them towards us, which maybe could have actually seeded water on Earth. But on the other hand, for the most part, Jupiter is making it so that there was less impacts. So you kind of go both ways. All right. So impacts can extinguish life, but they were necessary for life as we know it. All right. So was Jupiter necessary for life on Earth? Well, perhaps, right? Because if we hadn't had Jupiter redirecting comets, then really none of them would have come to us, which might mean that we wouldn't have water. Because one theory for why there is liquid water on Earth is it came from comet impacts. Okay. So in summary, did an impact kill the dinosaurs? Probably because the Iridium Layer is a strong suggestion. Plus, there's a crater that matches up. All right. Large impacts do absolutely happen, but they're rare. The scale is about 100 million years for mass extinction events. And the Jovian planets sometimes deflect comets towards Earth, but they send many more away out into the Oort cloud. All right, that's it. Thank you so much for this second video and all this content. I know it's a lot of content per chapter, but I hope it's been interesting. Thank you so much for watching this lecture video.